Okay, in this video, you're going to learn about how we calculate truss forces. Quick review first. Okay, remember in class we talked about reaction forces and moments. Okay, these are things that are happening to the overall structure, and when we talk about reaction forces, it's how the structure would respond when a load is applied. We don't want our bridge or our structure to actually move, so we want the sum of the moments to equal 0. We want the sum of the forces in the x direction to equal 0, and we want all of the forces in the y direction to also equal 0. Reaction forces happen at either pin supports or roller support. And a pin support is a structure that's going to be supported in 2 dimensions. A roller support is something that can only support in one direction. The purpose of calculating truss forces is to calculate the forces on a truss in order to accurately predict the type and amount of force each member must carry. There's 2 different types of forces that are going to happen on every beam. One is compression, so the body would be squeezed together, and the other one is tension, so the body would be stretched or being pulled apart. A truss is simply defined as slender members joined together at their endpoints. They're usually joined by any welds or gusset plates. If you look at this diagram, right there would be what's called a gusset plate. A simple truss is composed of triangles which will retain their shape even when they're removed from their supports. Take a look at a simple structure that's built without any kind of triangle shape. If I apply a force, that shape is going to distort or bend. By simply adding another beam or another support to create triangles, I created a much more sturdy configuration. When we solve for truss forces, there's some assumptions that we have to make. All members or all beams are considered to be perfectly straight. If we apply a load, we're applying it at the joint, not just randomly in the middle of a beam. Any joint is going to be a pinned connection, and it's going to be considered to be frictionless. And we also assume that each member has no weight. Now, we know that beams have weight, but that weight is going to be insignificant compared to any force or any load that's acting on that bridge. We also assume that members can only experience tension or compressional forces. Before we can do the math, we have to figure out whether we can do the math. To do that, we look at the static determinacy of a structure. A statically determinate structure is one that can be mathematically solved based on this equation. J is the number of joints, M is the number of members, and R is the number of reactions. Here's an example. Okay, so I want to take 2 times the joints. I have 1, 2, 3, 4 joints. Okay, so that would give me a value of 8 on the left side of the equation. Next, I'm going to count the number of members. There's 1, 2, 3, 4, 5 members or 5 beams. Then I'm going to add how many reactions I have. Okay, I've got 2 from here because it's a pin plus another 2. This equation doesn't work. I have 8 on this side and 9 on this side. All that means is that I would not be able to mathematically find everything about this beam. The way to fix that is to change one of those pin supports to a roller. Now this truss is statically determinate, and I'm going to be able to solve all of the variables that are acting, all of the variable forces that are acting on that truss. Here's another example. This is a bridge in Brockport, New York. It has 19 joints, 35 members, and 3 reaction forces because it has 1 pin and 1 roller. And that's going to make it statically determinate. So again, 2 times 19 gives us 38. 35 members plus 3 reaction forces gives us 38. If the numbers were different, what that means is that I can't mathematically solve for that truss. Okay, when I go to solve for the truss, we're going to use our equilibrium equations. Again, one of the first ones is the sum of the moments has to equal 0. So the sum of the moments about a given point has to add up to equal 0. Remember that to compute the moment of a pin, what we're going to do is we're going to take the force times that lever arm distance. Okay, so in this case, it would be 25 times 2 feet, or 50 foot-pounds, and it would go counterclockwise. A second equation that we take into consideration is the sum of the forces in the x direction. Anything acting to the right is going to be positive. Anything acting to the left is going to be negative. Our third equation that we're going to use is the sum of the forces in the y direction. Any vector that points up is positive, and a vector that acts down is negative. Okay, so I'm going to walk you through how we use the method of joints to solve for all of the forces acting on a truss. Time to have some fun. Again, as you're watching this video, take notes on that handout that I gave you. Okay, the first step when solving a truss is to re-sketch it or draw it out, and then also calculate any angles. Okay, so here's my truss redrawn. The first angle I'm going to find is the angle between triangle A, B, and D. Remember, when we find an angle, we do inverse tangent of our opposite side, over our adjacent side. Okay, hit pause, type it in your calculator, make sure you understand how I'm getting the angle of 53 degrees. I'm going to do the same thing for triangle BDC. I'm going to take 4 over 7, and I'm going to get 29.7 degrees. Okay, we're going to use those angles as we go through our problem. Okay, the next thing that I'm going to do is I need to find my reaction forces. Okay, based on the picture, point A is going to be our pin connection, and point C is going to be our roller. So I want to think about how this would twist or turn around point A when the force at D is applied. Okay, this whole structure would want to rotate around clockwise. We need point C to respond with the reaction force upwards. We also need point A to respond with the reaction force upwards. A would also respond by pushing in, or excuse me, pushing to the right as well. I need to find values for each of those reaction forces. To do that, I'm going to use my 3 equilibrium equations. Okay, so I'm going to start out and I'm going to sum the forces in the y direction. All of those have to equal 0, so anything up has to balance anything down. My reaction AY is up, CY is up, and I've got 500 pounds at point D acting downwards. As of right now, I'm stuck. I can't do anything because I have 2 variables. I'm going to try another equation, see if that gets me unstuck. Okay, so I'm going to do my moment. Anything counterclockwise has to be balanced with anything moving clockwise. So CY is my counterclockwise. I'm going to subtract that from that 500-pound force. That's 3 units away from my point. Now I can get a value for CY. That allows me to get unstuck with the sum of the forces in the y direction. So RAY is still unknown to me, but now I have enough numbers to solve for it. Okay, and finally, I'm going to do my 3rd equilibrium equation. So I'm going to sum the forces in the x direction. Anything acting to the right gets balanced with anything acting to the left. This time, I don't have anything acting to the left, so RAX comes out to be 0. I'm going to take a few moments and put all of those numbers onto my truss so I can kind of keep track of what's going on. Again, RCY equals 150, RAY equals 350, and RAX equals 0. Okay, the next task is to try to figure out the force acting on each of those beams. To do that, I'm going to start and pick a point. I'm going to select point D. Why? Just because I felt like it. Plus, it also has all of the forces acting in either the horizontal direction or the vertical direction, so I don't need to deal with any angles. To begin, I'm going to draw my free body diagram at point D. So I'm going to draw all of the forces that are acting at that point. Notice how I'm drawing all of my beams as pulling out or away from the point. What I'm doing is I'm assuming that all of these forces are acting in tension. The only reason I'm doing that is because I said so. I'm trying to make the problem as easy for you as I possibly can, and that's one way to do that. So always draw your arrows as if everything was in tension. Now that I have my free body diagram, I'm going to use my equilibrium equations again for each point. So I'm going to sum the forces in the x direction. We know that everything added together has to equal 0. Anything acting to the right gets subtracted with anything acting to the left. As of right now, I am stuck. I have two variables, so there's nothing I can do with that equation. That's another reason I wanted to start with point D, is because I wanted to show you, well, what do you do if you're stuck? The quick answer to that is move on and see if you get yourself unstuck. So now I'm going to sum the forces in the y direction. Anything acting to the right minus anything acting to the left. If BD is pulling to the right, or excuse me, is pulling up, and force of 500 is pulling down. FBD then comes out to be 500. It came out to be a positive value, which means that this is in tension. As I solve for these numbers, I'm going to add them to my truss so I can kind of keep track of what I've already found. Okay, so far I found that this beam, force BD, as I solve for each beam, I'm going to record that on my truss to kind of help me keep track. So I label the value and then also label it as compression or tension. As of right now, again, I'm done all that I possibly can at point D, so I'm going to move on and select another point. I'm going to select point A. So I'm going to do the same thing. I'm going to draw a free body diagram. Notice on our free body diagram that we draw all the forces of the members as tension, so they're pulling away from the point. Then my reaction forces, I just drew the direction that they would normally be going. I'm going to sum the forces in the x direction. Anything acting to the right gets subtracted from anything acting to the left. So I've got force AD acting to the right. I've also got this force that's at an angle that I need to deal with. Remember that any force acting at an angle can be split into its x and its y components. I need to make sure I'm including that in the sum of my forces. The x component of that force at an angle is adjacent to that angle, so it's going to be FAB cosine of 53. I also have FAX acting to the right, but remember when we solved for that, that was equal to 0, so it's not really going to influence the problem. As of right now, I'm stuck again. I have two variables. So I'm going to move on and see about summing the forces in the y direction. The reaction AY is up, and then I also have the y component of that vector that's at an angle. I have a value for that reaction force that we saw from before. So now I only have one variable. I can solve for FAB. Okay, typing it in the calculator, we get negative 438. The negative sign lets me know that my assumption was wrong, so this beam would actually be in compression. Solving for FAB allows me to come back up here and finish the sum of the forces in the x direction. Typing that in the calculator, doing a little algebra, you're going to get 263. This came out to be positive, so it's going to be in tension. I'm going to go back to my truss, and I'm going to add those two forces in. Okay, again, FAB came out to be 438 pounds. It was in compression, so I'm going to label it with a C. FAD came out to be 263 pounds, and that is in tension. Notice how now that I have FAD, I can come back to my problem from where I was stuck before, and I can finish this out. I can now solve for FDC. Okay, FDC is also going to equal 263. It came out to be a positive value, so that means it's in tension. Okay, I'm going to add that to my truss. Okay, notice hopefully that I only have one more force that I need to find. I found the force is acting on every single beam except for BC. So what I need to do is I need to do another free body diagram and do another set of equilibrium equations. I'm going to select point C because that way I only have one angle to deal with instead of two. Here's my free body diagram at point C. Okay, I'm going to do the same thing, sum the forces in the x direction.
I don't have any forces acting to the right. Everything is acting to the left. So I've got FCD acting to the left. And then I also have the X component of force CB. Force CB, okay, is going to equal FCD divided by the cosine of 29.7. Typing that in, I'm going to get a negative 302.7 pounds. Just like before, I'm going to write that into my truss. Came out to be negative, so it's also in compression. Okay, so what we're looking at is a complete problem solved for a truss. So we've solved for each reaction force, and then we've also solved for each beam. Come in with questions, and we'll deal with those in class.